Welcome to this lecture on the basic structure of a computer and the path from physical hardware to high-level programming languages. Our goal is to look beneath familiar applications and understand the layers that make them possible. We will begin with the hardware that receives input, stores information, performs calculations, and produces output. Then we will examine memory, storage, and the different forms computers take as technology changes. From there, we will discuss transistor capacity, programs, machine language, logic gates, assembly language, and high-level languages. The central story is one of abstraction. Each layer hides details from the layer above while preserving the capabilities needed to build something useful. By the end, you should be able to connect a line of source code to the instructions, circuits, and switches that ultimately carry it out. Inside the computer, hardware to high-level code by the programming professor. Here is our roadmap for the lecture. We will first establish the basic hardware loop, including the CPU, memory, keyboard, and screen. Next, we will compare fast temporary memory with slower persistent drives, and we will see how computer types have evolved from large shared machines to portable and embedded devices. We will then consider Moore's law and the hardware trends that make modern computing widespread. After that, we will shift from hardware to programs, beginning with machine language and the logic gates that implement computation. Finally, we will climb through assembly language to high-level programming languages. Notice that the outline itself follows a ladder: physical components, information movement, instructions, and human-readable programs. Keep that ladder in mind because it will help us connect the diagrams and examples throughout the presentation. Let us begin with the basic hardware loop. A computer accepts input, stores information in memory, processes instructions in the CPU, and sends results to output devices. The CPU is often called the brain of the computer, but it is useful to be more precise. The arithmetic logic unit performs mathematical and logical operations, while the control unit coordinates the actions of memory, the ALU, and input and output devices. When a user types a number, the value is placed in memory. The CPU reads it, performs an operation such as doubling it, stores the result, and sends that result to the screen. This simple pattern scales from a classroom exercise to a web browser or a scientific application. Programs are effective because they organize this movement of data and instructions. The CPU clock provides a shared rhythm for the components inside the computer. Conceptually, the CPU advances through instructions in synchronized steps, much like musicians follow a common beat. Clock frequency describes how many ticks occur each second. A gigahertz represents 1 billion ticks per second, so a processor with a higher clock frequency may be able to advance through instructions more quickly. However, clock speed is not the entire story. Faster switching requires more electrical energy, creates more heat, and can shorten battery life. Physical circuits and cooling systems also impose limits. This is an important engineering trade-off. Improving one measure of performance can create costs elsewhere. When comparing computers, remember that clock frequency is a useful indicator, but real performance also depends on the architecture and the work being performed. Now let us separate memory from long-term storage. RAM is the computer's fast working area. When a program is running, the CPU typically reads its instructions and needed data from RAM. The contents of RAM are temporary, so turning off the power causes those contents to disappear. A drive, by contrast, stores programs, documents, photographs, and videos even when the computer is turned off. Drives provide much more capacity, but accessing them is slower. The computer therefore moves selected information from the drive into memory before the CPU uses it. This relationship explains why adding memory can improve responsiveness. More of the active program and its data can remain in the fast working area. The basic pattern is speed in memory, persistence on the drive, and movement between them. Computer types have changed as technology has made processors smaller, cheaper, and more energy efficient. A server is designed to provide pages, files, or other services to many computers over a network. A desktop PC is a general-purpose computer intended for a home or office. A laptop keeps much of the same capability in a portable, battery-powered form. Tablets and phones specialize in mobility and combine input and output in compact devices. These categories are useful, but they are not rigid boundaries. Many devices now include computing hardware without looking like traditional computers at all. Cars, appliances, sensors, and toys may contain embedded controllers built for a focused task. Across all these forms, the architecture remains recognizable. Processing, memory, storage, input, output, and programs cooperate to perform useful work. Moore's law describes a long-running trend in integrated circuits. The number of transistors that can fit on a chip has grown dramatically over time. The graph on this slide is exponential, meaning that the amount increases by a repeated factor rather than by a fixed amount. Early growth appears gradual, but later growth becomes much steeper because each increase builds on the previous one. More transistors allow designers to place greater computing capacity into a smaller space. This trend helped make personal computers, smartphones, and powerful servers practical. It is important to treat Moore's law as an observation and engineering target, not as a guarantee that performance can grow forever without limits. Manufacturing difficulty, energy use, heat, cost, and physical size all create challenges. Still, the trend explains much of computing's remarkable expansion. Hardware trends have moved computing in two important directions. First, server farms concentrate large numbers of computers in specialized facilities. These systems provide web pages, video, storage, and software services to users across a network. Second, computing is moving outward into the environment through edge devices and embedded controllers. A sensor may process data near where it is collected, while a controller inside a car or appliance may perform one specialized job continuously. This means that many computers are now invisible to the user. They may have no traditional keyboard or screen, yet they still contain processors, memory, programs, and communication hardware. As you design software, ask where computation occurs and what constraints the device has. A cloud server, phone, and embedded sensor may run programs, but their performance, power, and storage requirements can be very different. At this point, we can shift from the machine's physical parts to the programs that direct them. A program is a sequence of instructions, and the CPU repeatedly fetches an instruction, interprets it, performs the requested operation, and advances to the next instruction. Data provides the values those instructions manipulate. The same hardware can act as a calculator, browser, game system, or text editor because the stored instructions change. This is one of the most important ideas in computer science. General-purpose hardware becomes flexible through software. The hardware supplies a set of operations, while programs arrange those operations into meaningful behavior. When you write a program, you are creating a plan that the CPU can execute. The plan may be expressed in a language designed for people, but it must ultimately become instructions the hardware understands. Machine language is the CPU's native vocabulary. The code example on this slide shows a short sequence of binary instructions that accepts two values, adds them, displays the result, and stops. The example is not intended to be memorized. Instead, notice that each instruction contains fields with specific jobs. Some bits identify the operation, while other bits identify memory locations or operands. The CPU follows the instruction set defined by its design and interprets each pattern accordingly. Machine language is compact and directly runnable, but it is difficult for humans to read and maintain. A single mistake in a bit pattern can change the operation entirely. This difficulty motivates the layers we will study next. Assembly language gives names to these operations, and high-level languages let programmers express larger ideas more naturally. Logic gates show how physical switches become useful decisions. A gate is a circuit built from transistors that implements a Boolean function. The NOT gate reverses its single input, a 1 becomes 0 and a 0 becomes 1. The AND gate produces 1 only when both inputs are 1. The OR gate produces 1 when at least one input is 1. Each gate hides the details of the transistors inside it, giving designers a simpler component to combine with other components. This is another example of abstraction. We do not need to reason about every electrical change when we want to build a larger circuit. Instead, we can reason about inputs and outputs. By connecting many gates, engineers construct circuits for mathematics, memory, control, and the instruction processing performed by a CPU. Truth tables make the rules for logic gates explicit. Each row lists a possible combination of input values and the output produced by a gate. For an AND operation, only the row with 2 ones produces 1. For an OR operation, every row with at least 1 1 produces 1. A table like this may look simple, but it provides an exact specification that can be implemented in hardware or used to reason about a program condition. Larger circuits are built by connecting the output of one gate to the input of another. An adder, for example, combines logic operations to calculate a numerical result. In software, Boolean expressions use the same basic ideas to choose between paths. Whenever a program tests whether several conditions are true, it is applying rules that have a direct connection to physical logic. Assembly language adds a human-readable layer above machine language. Instead of writing a raw bit pattern, a programmer can use a short operation name such as add along with symbolic memory locations. An assembler translates those names and operands into the binary instruction pattern the CPU can execute. The diagram shows this translation from an assembly instruction to a machine instruction. Assembly remains close to the hardware, so it can expose registers, memory addresses, and precise operations. That control can be valuable when performance or hardware access matters. At the same time, assembly programs are more detailed and less portable than high-level programs. The important historical step is that assembly does not change what the CPU can do. It changes how humans describe the same underlying operations, making the instructions easier to inspect and construct. High-level languages raise the level of abstraction again. The short example on this slide reads an input, computes a value using a variable, and prints the result. It expresses the programmer's intent directly rather than naming individual memory locations or binary operation fields. A compiler translates high-level code into lower-level instructions, often passing through assembly or another intermediate form before producing machine code. One readable statement may require several lower-level instructions, because the compiler must handle storage, mathematics, control flow, and input or output details. This translation gives programmers much greater productivity and makes programs easier to share across different kinds of computers. Languages such as C, C++, Java, Python, and JavaScript offer different strengths, but they all rely on the same general idea. Human-oriented notation is translated into operations that hardware can perform. Let us summarize the path we have followed. At the hardware level, the CPU, memory, input devices, output devices, and storage work together. The clock coordinates instruction steps, RAM provides fast temporary storage, and drives preserve information. Transistors form logic gates, and gates combine into the circuits that implement computation. At the programming level, machine language gives the CPU exact bit patterns. Assembly language replaces those patterns with readable operation names. High-level languages let us describe useful algorithms and data transformations without managing every switch directly. These levels are not separate worlds. They are connected layers of one system. When a program behaves unexpectedly, understanding the layers can help us locate the cause. Programming works because abstraction allows us to build meaningful behavior on top of physical switches. Thanks for watching. Let me know in the comments if there are other topics you would like me to talk about. If you enjoyed this video, please like, share, and subscribe for more content on software engineering and technology. See you next time.